Welcome to today's class. We have been discussing the solar system. Today we are going to come back closer to the earth and discuss the moon, earth moon orbit in particular, and its influence on the earth. And the moon, as we know, is the most prominent astronomical object in the night sky. So, the earth moon system is what we are going to discuss today. The mass, this shows you a picture of the moon, and you can see that there are all kinds of, it appears as a white circular disk on the sky, but it is not uniform. There are craters on the moon which you can see over here. So, the moon has its own structures on the surface. The mass of the moon is considerably smaller than the mass of the earth. It is 7.3 into 10 to the power 22 kgs, whereas the mass of the earth is considerably larger. It is around 6 into 10 to the power 22 kgs. But the radius of the moon is comparable to the radius of the earth. It is around 1/4. And if you calculate the density of the moon, it comes out to be roughly of the order of half of that of the earth. Okay. Now, if you look at the orbit of the moon around the earth, so the moon is orbiting around the earth, then the average distance from earth is 384,400 kilometers. It is a very small fraction, 1/4% of the distance between the earth and the sun. So, the orbital radius of the moon is much smaller than the orbital radius of the earth around the sun, and this gives you the nearest distance of the moon from the earth. And the orbit has an eccentricity again which is quite small. So, the orbit is nearly as good as circular. There are small variations in the distance, but not large. Okay. And the orbit is inclined by a very small angle, 5.145 degrees to the ecliptic. So, the orbit of the moon is nearly coplanar with the orbit of the earth around the sun. So, they are more or less coplanar. There is a very small angle between the orbit of the moon and the orbit of the earth, right. And the sidereal orbit period, by sidereal orbit period we mean that the moon comes back to the same position with respect to the fixed stars, okay, not with respect to the sun or something else, but with respect to the fixed stars. And this is the time it takes to complete one orbit, and this is 27.3 earth days. The moon also rotates around its own axis, and the direction of rotation is the same as the the rotation has a period, the sidereal rotation period, that is the time again it rotates, does one rotation with respect to the fixed stars, that again is 27.3216 degrees. And the rotation and the revolution of the orbital motion of the moon are in the same direction. So, we always see the same face of the moon. Okay. The rotation direction and the orbital motion of the moon around the earth are aligned, are in the same direction, and so we always see the same face of the moon. And the equator of the moon, equatorial inclination angle, so the equator of the moon is inclined to the orbital plane by a small angle again of 6.68 degrees. Okay. So, these are a few of the parameters of the moon's orbit around the earth. Let us briefly touch upon the question, how did the moon, we have learned how the solar system originated. Now, let us briefly touch upon the question, how did the moon originate? It is believed that it possibly formed by the impact of a Mars sized body on the earth. Okay. So, an object comparable to the Mars possibly collided with the earth, and this collision led rise to debris, and some of it got scattered off the earth and in that impact, and one of those debris is the moon. Okay, so there was some collision, and so it is basically material from the earth and the object that collided with the earth. So what remains on the earth is a mixture of those two objects, and a part of that splintered off and gave rise to the moon. That is what is believed, but I mean these are open issues possibly still. Okay. Now, the orbit of the moon around the earth has a very interesting consequence. The sun, you can think of the sun as being located very far away. So, the rays of the sun are more or less parallel, and they illuminate half the one face of the moon always, well, more or less always. So, one face of the moon is always by and large illuminated by the sun. Now, the moon also rotates around the earth, and depending on the position of the moon relative to the direction of the sun, we only see a part of the illuminated face, we do not see the entire illuminated face. For example, when the moon is in the same direction as the sun, then the part that is illuminated is completely away from us. So, we only see the dark side of the moon, so we do not see anything, that is called new moon. And when the moon is in the direction opposite from that of the sun, completely opposite, then we see the entire face that is illuminated, and we have the full moon. Okay. And in between we have these phases. So, this is called the first quarter, and this is called the third quarter. In Indian tradition, one is called Shukla Paksha and the other is called the Krishna Paksha. So, here the moon, you see larger and larger parts of the moon illuminated till the full moon, and then again the part that is illuminated gets reduced till a new moon occurs. Okay. And these are the different phases of the moon. Okay. And the time period for this to happen is not exactly the orbital time period. The time period for this to happen, it is called a synodic month. Okay. The month is the definition, the month actually is decided by the one lunar cycle, and this is called a synodic month. It is 29.53 days. So, it is slightly larger than the orbital period of the moon, the sidereal orbital period. And this difference is because of the fact that the earth is also moving with respect to the sun, revolving with respect to the sun. So, the sun is not at a fixed position. In this picture, the sun is at a fixed position, earth is fixed, and the moon just goes around, then the period would be exactly the orbital period of the moon, but the earth itself is revolving around the sun. So, the direction of the sun also changes, and as a consequence this is different from the sidereal lunar orbital period, which is somewhat smaller, 27.32 days. Okay. In addition, the phases are not exactly this much. There are perturbations due to the other planets. Okay. So, the gravitational effect of the other planets, other astronomical objects in the solar system have an effect on this. This again causes some variations. Okay. Now, the moon and the sun, if you ask the question, what angle does the moon subtend on the sky? Well, you could easily determine this. You could just extend your hand out like this and see how many fingers you need to block out the moon. It is safer to try it with the moon than the sun. So, you could see how many fingers do you need to block out the moon, and the ratio of this, the number of fingers that you need to the length of this will give you the angle the moon subtends in radians, and you can convert it to degrees. Okay. So, I advise you to try out this exercise at night. And if you do this, you will find that the moon and the sun, you will find that the moon subtends approximately half a degree, and the sun also subtends approximately the same angular extent on the sky. So, the sun and the moon both subtend approximately half a degree on the sky. Okay. So, now if you look at this picture, the sun is over here in this direction. So, you could imagine that whenever the moon comes in between the earth and the sun, the moon would completely block out the sun. Okay. And again, when the moon would be on this side, the earth's shadow is large enough to completely cover the moon, right. The earth is bigger than the moon. So, it would subtend a larger angle at the moon than the sun, and the earth's shadow is big enough to completely block out the moon. So, the earth's shadow would completely block out the moon over here. Well, if this happens, you have what is called an eclipse, and if the moon blocks the sun, then it is called a solar eclipse, and if the earth's shadow completely falls on the darkens the moon, then it is called a lunar eclipse. And we had a solar eclipse just a few days ago. I do not know if all of you are aware, but just a few days ago we had a solar eclipse. Okay. This shows you a picture of the total solar eclipse of 1999. Right, the sun, the disk of the sun is more or less completely blocked by the moon. You can see very small parts of it here. Okay, what you see outside is something else. It is not the disk of the sun. It is something associated with the sun, the corona, but not the disk. Okay. Now, you could naively think that you would have an eclipse twice every month, right. The moon goes around the sun in a month, in a synodic month, and once you would have a solar eclipse, once you would have a lunar eclipse. But that is not true, because the plane of the orbit of the moon is inclined, right. We have seen that it is inclined to the orbit of the sun, to the ecliptic orbit. So, it is inclined to the plane in which the earth is going around the sun. So, they are not always coplanar, they are approximately coplanar, but not okay. So, the moon is in a position to block out the sun, or the sun's shadow will fall on the moon only when the moon is close to the ecliptic plane. So, when the trajectory of the moon is close to the ecliptic plane, only then is there a chance of an eclipse, and this occurs twice a year. Okay. So, the orbit of the moon is fixed, you can think of it, and the sun is moving in the ecliptic. So, it will cut the two orbits will intersect only twice a year. And so, whenever the moon is around that region, you will have eclipses, and you roughly have 4 to 7 eclipses every year. Not all of them are very significant. Sometimes there are total eclipses, but by and large they are quite insignificant ones, partial eclipses. Okay. So, that is the rough figure for eclipses, and what we learn from this is that these eclipses will occur near the node where the lunar orbit intersects the ecliptic plane. That is the region where you will have eclipses. You will not have eclipses in all parts of the sky. Okay. We will now consider another very interesting consequence of the fact that we have this satellite, the moon, going around the earth. Okay. And this is the fact that you have tides in the sea. So, this picture shows you that it is a picture of a place called Fundy Bay, and it shows you the bay, the same location at high tide, where the level of the water is high, and at low tide where the level of the water has gone down considerably and it is quite far away. Okay, the level of the water has gone down considerably and the sea has receded quite some distance. Okay. So, the tides are refer to the fact that the level of the sea goes up and down during the duration of a day. Okay. And if any of you have been to this place called Chandipur, which is in around 120 kilometers from here in Orissa. In Chandipur you have very spectacular tides in the sense that the water, the coast is very shallow, extremely shallow. So, the sea recedes a few kilometers at low tide and it comes up a few kilometers at high tide. So, you can see the sea. If you go there during a low tide, you will be hard to imagine that there it is, you are on the sea coast. The sea will not by and large not be visible. It will be audible but not visible. Okay, but at high tide you will find that place underwater. Now, there are different types of tides. Let me just spend a little time discussing this. At most locations, at most places on the coast, you have what are called semi-diurnal tides. So, this picture, the graph, the y axis shows you the water level at the coast, at some point along the coast, it shows you the water level. Okay. What is important is that the water level for our purposes rises and falls and rises again, it is a periodic thing. And in this semi-diurnal tide, it rises and falls by approximately the same amount every time. And if you can make this out, this is a tidal period. So, the time duration between two maximas is the tidal period. And okay. So, this is a tidal period and one tidal day, okay, one tidal day, you see this from here to here is one tidal day. So, in one day the tide rises up once, then goes down, rises up again and then goes down. So, you have two periods in one day, that is why it is called semi-diurnal. Okay. So, you have high tides or low, the tide repeats, tides repeat approximately every 12 hours. Okay, I shall give you the exact figure later, but so that is what happens in most locations. This is called semi-diurnal tide. Now, you could also have what are known as mixed tides. Here again the tide, the water level rises up and down every approximately 12 hours, twice a day, but the amplitude is not the same. So, once the amplitude is larger and the other time the amplitude is smaller, again that repeats. So, it is not exactly periodic in 12 hours, there is a 24-hour period, but the water level does go up and down every 12 hours, approximately 12 hours. And then you have diurnal tides where there is a 24-hour variation in the water level of the sea. So, let us ask the question, what causes the sea level to go up and down? Okay. What is it that causes the sea level to go up and down? To understand this, let us do a small calculation over here. And the thing that we are going to calculate is as follows. Consider a spherical object, could be a planet, could be the moon, could be the sun, of mass m, and there is an test particle here, let us call it A. which is falling freely in the gravitational field of this massive object. Okay. So, it is falling freely in the gravitational field of this massive object. And let us consider the situation where there is an observer sitting on this. So, you are sitting on this A, okay, and you are observing another object B which is also falling in the gravitational field of the same massive object. This object B, this particle B is at a distance r. So, this distance to A, let us call it capital R, and this distance is small r. So, capital R is the distance from A to the center of this mass, okay, that is capital R. So, the observer A is located at a distance capital R, and both of these, okay, and the particle B is at a distance which is r less than that of A. And the question that we are going to ask is, suppose there is an observer sitting here who is falling freely in the gravitational field, what is the relative acceleration that he will see for B? Sitting here, what is the acceleration of B relative to A? Okay. So, at what is the second time derivative of this distance r? That is what we mean by the acceleration of B relative to A. Okay. So, let us write down the equation of motion for B relative to A. So, d square r dt square. Now, we know that the gravitational acceleration is the same independent of the mass, that is called the equivalence. Let me just spend a minute discussing this. This is the equivalence principle. So, there is an object here mass m, and there is another object of mass small m, let us say. Okay. One of them need not be small, not required. Okay. They may be same, m, this may be larger than this, does not matter. Let us write down the equation of motion of this particle, this object in the gravitational field of this. So, the equation of motion, let me call this vector r of this object is m mass of this into the acceleration will be equal to minus g, the mass of the two objects which produce the gravitational field, into 1 by r square, and I can write that in vector form, or let me, there is no need to write it in a vector form, we can write it like this, right. So, that is the equation of motion for this particle, and it is going to move radially, that is the direction. Okay. Now, the point to note is, when I write the equation of motion of this particle, the same mass of this particle appears on both the left hand side and the right hand side. So, I can essentially cancel it out, and what I can say is that the acceleration is this. It does not depend on the mass of this particle, it only depends on the mass of the other particle that is producing. So, for this particle, this is producing the gravitational field, so it will only depend on this mass. Similarly, if I write the equation of this mass, its acceleration will only depend on the other mass, not on this mass. Okay. This is called the equivalence principle. It is a very important property of gravity, and the whole of the theory of general relativity is based on this equivalence principle. Okay. So, the acceleration that this body experiences does not depend on the mass on its own mass. Okay. So, with this let me come back to the calculation that we were doing. So, we are writing the acceleration of B with respect to A, right. So, the acceleration of B with respect to A, we will first write the acceleration of B with respect to this object, that is going to be minus Gm by r minus r square, right. That is the acceleration of B with respect to this, and I have to subtract out the acceleration of A because my observer is sitting on A. Sitting on A, what is the acceleration I see for B? So, if I subtract this out, I will have to add plus Gm by r square. Okay. And the right hand side can be written as minus Gm by r square, right. I am writing this term as Gm by r square. Then I have 1 plus r 1 minus r by r whole square minus 1, right. I can write it like this. The first term will be minus 2 here. Okay. The first term is nothing but this, the second term is this. Okay. So, I have written the denominator over here as 1 plus small r by capital R to the power minus 2. Okay. And we are going to assume that this distance is much smaller than the distance of both these objects from the gravitating mass, right. We are going to assume that the small separation r is much smaller than this separation, and as a consequence of this we can do a Taylor expansion and keep only the first term in the Taylor series. If you do that, then this 1 will cancel out with this 1, and what we are left with is that this is equal to 2 G m into r by r cube, right. I am doing a Taylor expansion in this. So, the first term is going to be r, second term will be plus 2 small r by large R, which gives me this when I multiply it here. The 1 will cancel out with this. Okay. So, this is the acceleration of B relative to A. Okay. So, what do we see? We see that an observer in A who is falling freely in the gravitational field of this object will see another object B which is also falling in the gravitational field of this object accelerating away from him. Okay. Why does this happen? It happens because the gravitational attraction here is less than the gravitational attraction here, right. So, if I am falling here and if another object is falling here, this is accelerating faster, this is accelerating faster, not less, more. This is accelerating more than I am. So, I will see that it is accelerating away from me. Okay. So, this is what we find. Similarly, if I had done the same exercise for another observer, for another test particle C over here, again I would have found that C also will accelerate away from me with the same acceleration. Now, it will be away. Okay. Why will this happen? If I repeat the same calculation for C, I will find that it accelerates away. Why is this so? Because C is accelerating, its acceleration of C is smaller, less than that of B. So, if I sit on B, I will see that C is accelerating away. Okay. So, what happens is, if I sit on A, I will find that these two test particles, which are falling in the same gravitational field, are both accelerating away from me. I am falling freely, they are also falling freely. I will see that they are accelerating away from me. Okay. And to first order in this small r by capital R, it is given the difference, this is, it is given by this. Let us repeat the exercise now, but let us now, okay, let me draw the picture first. Let me now consider the same situation. So, there is this guy at a distance r from this big massive object falling freely, and he is now observing another test particle which is not located radially, but is located in the transverse direction. So, let us call this D, sorry, this was A, right, let us call this D. So, here I was sitting on A and looking at B and C. Here I am looking at sitting at A again and looking at D, which is in the radial transverse direction. Okay. Again, to find the relative acceleration between this and this, I have to subtract out the acceleration, I have to take the acceleration of this and subtract out the acceleration of this. Okay. So, let me call this R. Okay. Now, the point here is that this acceleration and this acceleration are in different directions. Okay. And if I call this direction x and this direction y, then the acceleration of D will be so it will have two components. The magnitude is going to be minus g m by r square. R square is this distance. This distance is the sum of capital R plus this distance between D and the mass center of the mass is, you can apply Pythagoras' theorem, it is the sum of this squared plus the sum of this squared square root. We are working only to first order in this small distance. So, the extra correction we can ignore. Okay. So, this is approximately in the approximation that we are working. The magnitude of this acceleration is g m by r square. Okay. But the direction is not, what is the direction? Let us see. So, there will be one component of direction along the minus x direction, one component along the minus x axis. So, there is a minus sign already there, and that component is going to be cos theta, where theta is the angle that this makes with this, and cos theta again is second order in this divided by this, right. Sin theta is small r by capital R. Okay. So, we can say that the angle, this is going to be this into I minus sin theta, which is r by r j. Okay. And we have to subtract out the acceleration of A. So, we have to subtract out g m by r square actually it would have been better if I had taken my y axis instead of taking it like this. If I had taken it like this, then this will be a plus sign and this r would also be along the plus y direction. Okay. So, this is a better convention. Now, when you subtract out, when you add these two components, what you are left with is that d square r dt square is equal to minus g m by r cube into r, and this is only along the y direction, the x component cancels out. Okay. So, the y direction is here instead of here, and the x, so the x component of these two forces cancels out, there is only the y direction and it is directed opposite to this direction of the displacement. That is obvious from these two pictures or from this picture also. These two tend to converge, so the difference in the acceleration is going to be inwards. Okay. So, these forces, so let me summarize what we have learnt. What we have learnt, let me summarize what we have learnt here. Okay. So, we have these forces called the tidal forces, and if my, so there is a sphere like this, or you can think of particles in a circle or a sphere like this, and they are falling freely in the gravitational field of a massive object which is located down, somewhere straight down. Okay. So, the center of mass of this falls freely gm by, so if I sit in the center of mass, I will see that the particle located over here is accelerating away from the center of mass with an acceleration 2 gm by r cube, gm r by r cube, where r is the distance from here to here, center of mass to here, and r is, capital R is the distance to the massive object. Okay. And similarly, in this direction also there will be an acceleration away, whereas in the tangential directions there will be an acceleration inwards, relative acceleration, and these will have magnitude gm into r by r cube, gm into r by r cube. Okay. These are called tidal forces, and if a spherical object, if such a spherical object falls freely in such a gravitational field of a massive object somewhere down below, these forces will try to deform this object into an ellipse like this. Okay, so this is the consequence of tidal forces. Now, so these tidal forces are what are responsible for the level of the sea going up and down. Okay. What are the, so there are, see the earth is falling freely in the gravitational field of two massive objects. One of them is the moon and the other one is the sun. Okay, so earth moves freely in the gravitational field of the moon and the sun, right, and it is the sun which we know determines the orbit of the earth. The motion of the earth is largely, center of mass of the earth is largely governed by the sun, the gravitational field of the sun. Okay. Now, the sun and the moon both also exert tidal forces on the earth, and these tidal forces occur because, essentially because the earth is an extended object and the gravitational field is not uniform. Okay. And the tidal force, what it does is it will try to elongate, deform the earth something like this. So, when the sun or the moon, say the sun is located below or the moon is located below, then it will try to deform the earth like this. Now, the earth, so okay, so the earth is a solid object, and if you apply such forces, it's an elastic, you can think of it as being elastic. So, it will deform to some extent, but the water on the earth's surface can flow, and under the influence of such a force, the water, 75% of the earth's surface is covered by water. So, the water will move towards these. So, when the sun is exactly below or overhead or the moon is exactly below or overhead, the water on the earth's surface will accumulate, will rush towards these 2 points and it will move away from these 2 points. Okay, so, these points will have low tide, these points will have high tide. Now, let us, so I have told you broadly what the what causes the tides. Now, let us try to estimate which one is more, which influences more, the sun or the moon. Okay. So, let us see. So, let us first take up the tidal force of the moon. On the earth. Okay. So, tidal force produced, tidal acceleration produced by the moon on the earth, and we can estimate this by calculating g into the mass of the moon, radius of the earth divided by the earth moon distance cubed. Okay. So, let us put in the values of capital G is 6.67 into 10 to the power minus 11 in SI units. Okay. Then the mass of the sun we have just seen, it is 7.3 into 10 to the power 22 kg. We are working in SI units throughout, so I will not write the units. And the earth moon, the radius of the earth is 6.4, 6,000 kilometers, so in meters. Okay. And I have to divide this by the radius of the moon's orbit around the earth, which again we have just seen, it is 3.8 into 10 to the power 8 meters. So, I have to cube this, and this will come out to be in units of acceleration, meters per second square. And if you do this calculation, if you just do this division, what you get is that this comes out to be okay. So, it is a very small fraction, it's very small compared to the acceleration produced by the earth on its surface. What is the acceleration produced by the earth on its surface? 9.8 meters per second square. Okay. So, it is extremely small compared to that. The acceleration, the difference in the acceleration produced by the moon. Okay. Similarly, now let us estimate that for the sun. So, the sun, what is the tidal acceleration that it produces on the earth? So, let us 6.67 into 10 to the power minus 11 into the mass of the sun. We have seen the mass of the sun, it is 2 into 10 to the power 30 kgs into again the radius of the earth 6.4 into 10 to the power 6 meters divided by the cube of the earth sun radius, and the earth sun radius, one astronomical unit is 1.5 into 10 to the power 11 meters. So, this cubed, and what you get is 2.5 into 10 to the power minus 7 meters per second square. So, that is very interesting. Two things that we have to note. The first is the fact that the moon produces larger tidal effects than the sun, okay, roughly twice, even though the moon is much smaller in mass than as compared to the sun. Since this effect goes as 1 by r cube instead of 1 by r squared, the moon is nearer, so it produces a larger tidal force than the sun, tidal acceleration, and the tidal acceleration is much less than the the overall acceleration produced by the earth itself on its surface. Okay. So, let me just remind you what we have. So, if you consider a test particle here on the earth's surface, there is one acceleration produced by the earth, that is 9.8 meters per second square, acting inwards always. Okay. and there is another acceleration produced by the moon. If the moon is exactly overhead or exactly below, that acceleration is going to be 10 to the power minus 7, something into 10, 5.6 into 10 to the power minus 7 meters per second square. Okay. But that acceleration has a different pattern on the surface. It is inwards in along the direction perpendicular. So, if the moon is up here or down here, see, it is symmetric. If the moon is up here or down here, then the acceleration is outwards along the direction of the moon, it is inwards perpendicular to the direction of the moon. Okay. And it is the moon which produces the major effect, the bigger effect. The sun produces a smaller effect. Okay. So, in most places, okay, or the main constituent of the tidal forces, the principal lunar, it is the principal lunar diurnal, okay, and it has a period of 12 hours 25 minutes. Okay, so that is the moon. So, if the moon is overhead, the tide, we have high tide. If the moon is exactly below, again we have high tide. It is a 12-hour period. Okay, and the period is not exactly 12 hours, which is slightly more, because the lunar orbit is in the same direction as the Earth's spin. The moon does not remain fixed in the sky. Okay, it does not remain fixed, it also moves, and it moves in the same direction as the Earth spins. So, it will take more than 12 hours. The Earth will spin exactly half in 12 hours, but the moon has moved by then. So, it takes slightly more than that. Okay. Now, there are other effects. So, these effects are the sun's gravity, these are lesser effects. Then we have the inclination of the Earth's spin and the moon's orbit, these are all inclined with respect to each other. There are also variations in the coastline which contribute to the differences in tides in different places. Okay. So, if the picture were as simple as what I first told you about just the moon causing the tides, you would have a 12-hour 23 minutes tide everywhere, but there is also the sun which causes it to vary from time to time, and the orbits are inclined. Further, it also is influenced by the coastline. So, the coastline is different in different places, and that also has an impact on the tides. Okay. So, all of these together shape the tides, and tides are extremely important. You can see the tide in the Ganga, for example. The sea level at high tide, the sea level rises up, and this causes the level in the Ganga to also rise up, and the whole thing moves upstream. Okay, so even in Kolkata, you can see the influence of the tide. The sea level will go up, and the level of the Ganga will also rise as a consequence. Okay, so you can see it in Kolkata, and if you go to the sea coast, it is quite obvious. Okay, it is very important for shipping and various other activities. If you are going swimming also, and now you have something called spring tide and neap tide. So, what are spring tide and neap tide? Now, the moon is going around the earth, and it is this that we have seen is the major constituent of the tides. So, when the moon is over here, when the portion of the earth that is exactly below the moon will experience high tides, or okay, so there are two places which are exactly below the moon, this place and this place, and you will have high tides in these places, and when the moon is at 90 degrees you will have low tides, right. That is the nature of the tidal force. That is what we saw. No, sorry, yeah, that is right. So, you will have a high tide here. So, when the moon is overhead, the force is outwards and it will pull the water up, and you will have high tide. When the moon at this location, when the moon is at 90 degrees, the the effect of the tidal force is to push the water inwards away, and you will have low tides. Okay. Now, the tidal force of the moon is reinforced by the tidal forces of the sun when the moon and the sun are aligned, when they are in the same line. Okay. And this is the line joining them is also called C. That is the name given, alignment of the sun, moon and the earth. So, when you have this syzygy, the tidal force of the sun reinforces the tidal force of the moon, and the tide really is much higher, the tide level really is very high. You have what is called a spring tide. Okay. So, when the sun, the moon and the earth are aligned, so that can happen either at new moon or at full moon or new moon, both of them. The sun and the moon are aligned. So, the tidal forces of the moon and the sun are aligned also, and you have a spring tide. So, it is like a spring, it springs forth the tide. Okay, you have quite a high tide. Whereas, when you have the first quarter or the third quarter of the moon, the tidal forces of the moon and the sun, they cancel each other, and you do not have such very high tides, such severe tides. The tides are less. So, the amplitude of the tides will be less. So, at spring tide, the high tide is going to be very high, the low tide will be very low. Whereas, at neap tide, that is called a neap tide. At neap tide, the high tide will not be so high, the low tide will not be so low. So, if you want to see spectacular tides, you will get them during the new moon or the full moon. Whereas, in the first quarter or in the third quarter of the moon, when the sun and the moon are perpendicular, the tides will be there, but they will not be so severe. Okay. So, we have learned how the moon causes tides on the earth, but these tidal forces are quite ubiquitous. Okay. So, there is something, let me discuss another phenomena where tides could be important. So, this is an issue that was first looked at by Roche. But I shall first discuss it in general terms, and then we shall look at the particular application that Roche had in mind. So, consider a big massive object over here of mass m, and there is another smaller massive object of mass, let us say small m, and the distance between these two is r, and the radius of this small massive object is r. Okay, that is the radius of this small massive object. Now, let us assume that this is gravitationally bound. It is not bound by other interactions. I am not gravitationally bound, I am bound by electromagnetic forces, right. This table is bound by electromagnetic forces, different bonds. But let us assume that the sun is gravitationally bound. Okay. Or so, let us assume that this object over here is gravitationally bound. Gravitation is the dominant force which holds this object together. Okay. Now, this object over here will experience the tidal forces due to this big massive object, and there will be the tidal forces will try to pull this object apart along the radial direction. So, the tidal forces will try to pull it apart here like this, and it will try to compress it like this. That is what we have seen. Okay. Now, there will be a distance, and if you bring this object closer than that, then the tidal forces will be more than the gravitational forces that hold this object together. If this happens, then this object will be tidally broken. right, the tidal forces will exceed, like we on earth we saw the tidal forces of the moon and the sun are extremely small compared to the acceleration provided by the earth. Okay. But if it may so happen that if you bring this object sufficiently close to this big massive object, there will be a certain distance where the tidal forces are sufficient to disrupt it. So, let us see, let us estimate that distance. Okay. So, that distance, the tidal force which is trying to pull it apart is 2 g m, sorry 2 g, then the radius of this object r by r cube, right. That is the tidal force which is trying to pull this object of radius small r apart. That is a radial tidal force. And the gravitational force exerted by this small object on itself, on its surface, is going to be g m by r square. And we would like to see where these two forces are balanced. And it is quite obvious from this that these forces will be balanced if r is equal to 2 m by m into r. Okay, this is called the tidal radius. So, for this object of mass small m and radius r, if I bring it closer than this distance, if we bring it nearer than this distance, it will be disrupted by the tidal force. Okay. So, if it enters a distance smaller than this, it will be disrupted by the tidal force. And we know that these Jovian planets like Jupiter, Saturn, Uranus, they have rings. So, Roche was investigating the possibility that these planets could have had satellites which came closer than the tidal radius, and these satellites got disrupted because of the tidal force, and then the small debris collided and formed these rings. Okay. The size of the ring, the particles in the ring are of the order of centimeters to decimeters. Okay. So, I will request you, this is something that you have to do, assignment, and you should give a written report on this. Please read up on the possibility that you can form rings by the disruption of planets, form rings around planets by the disruption of satellites through tidal forces. Okay. So, read up on this, how, whether it is possible to form rings around planets by tidal disruption of satellites. This was a thing that was investigated by Roche, and he arrived at this interesting concept of a tidal radius, which has applications in various other situations also. Okay, so let me stop here, and in the next class we shall consider something else.